Welcome back to Math 320 videos. In this final lecture from week 8, we will introduce the notion of continuity for functions. For some of you, this may not be the first time seeing this concept. If so, great! I hope this review will be useful. If this is the first time for you seeing this, that's also okay. I'm including lots of examples today so you can get a better feel of what continuity proofs look like. A lot of what you will be doing in this lecture will feel a lot like the sort of arguments you already did for sequences. This is intentional. We're trying to build up your ability to reason about continuity concepts so that you can do them almost like second nature. Next week, we will dive more into the continuity concepts and their properties. For that, we will be doing somewhat more abstract reasoning concerning continuity, tying it together with some of the ideas we mentioned previously with sequences and limits. So it will be definitely more approachable next week if you can develop some good habits about reasoning with continuity issues now. Okay, enough introduction. Let's get into it. Oh, right. This lecture covers material from pages 123 to 127 of your textbook. Let's start with a version of the definition of continuity. This is the one probably you are most familiar with from calculus or college algebra. It says that for a function defined on an open interval AB, if C is a point in the interval, then f is continuous at C means that f of C is equal to the limit of f at C from below and is equal to the limit of f at C from above. This string of equality can also be summarized as saying simply that the limit of f at C is equal to f of C. The limit of f at C being something only defined when both the limit from above and the limit from below exist and are equal. Notice that we require C to be in an open interval a to b. This definition here requires that it makes sense to take a limit from above and a limit from below. In our definition earlier this week, the limits from above and below are defined when f is defined on an open interval immediately above or below the point being considered. These technicalities aside, we see that essentially continuity of a function represents simply the expectation that the value of the function at a point C is the same as the limit you get when you evaluate the function at nearby points and bring the points of evaluation closer and closer to C. Remember that when we defined the limit of f at C earlier this week, the value of f at C is not involved. So, the continuity concept is basically extending the limit concept by adding the requirement that now not only should the limit exist, but the limit should equal to what the value of the function is at that point. A slightly more flexible version of the definition is given here. Now, we let f to be a function whose domain is some set S. This set is no longer required to be an open interval. It can be any subset of the real numbers. We take a point C in S. We say that f is continuous at C if, for every epsilon positive, there exists a delta positive such that for every x that is both in the interval C minus delta to C plus delta and in S, we have that the difference between f of x and f of c is no more than epsilon. In effect, we are cutting out the limits middleman here and fully expanding the definition. Since for continuity, we need a limit to equal the value of the function at c, we can replace the arbitrary L in the limit definition with f of c. Independently of the limits definition, we should look at this definition and try to understand what it is saying. The notion of continuity it is describing here is in terms of tolerances. Think about a function as a bit of a black box that if you put in some number, it spits out a number on the other end. Suppose you have some requirement for the output. Say you want the output to be exactly some number, but you have some degree of tolerance, so you can accept the output to be that number plus or minus epsilon. These kinds of tolerances are frequently encountered in applied sciences. You want to know what is the amount of error you can have for the input and still get an output that falls within this tolerance. The allowed amount of error for a continuous function would be the delta. So what would be a discontinuous function? This would be one that is so sensitive to changes in the input that a tiny change in the input can have a ruinous effect on the output. Kind of like a cliff. If you go over just a tiny bit, you will fall off to the bottom. So, an interpretation of the epsilon delta definition is that a continuous function is one that has built-in tolerance for errors, and a discontinuous function is one that does not allow errors. One additional advantage of this definition is that it is much more flexible when it comes to the domains. The limit definition we gave before requires the domain to be an open interval containing C. Here, we have different choices. If the set S has C as an endpoint, say S looking like a half-open interval with the endpoint C closed, then our definition of continuity in terms of epsilons and deltas reduces to the appropriate limit definitions. If we have a half-open interval from C to B, then the definition is the same as saying that f of C equals limit from above at C. If we have a half-open interval from A to C, then the definition is the same as saying that f of C equals the limit from below at C. If the domain is an entire open interval around C, then the definition is the same as saying that f of C equals to limit of f at C. So this epsilon definition, so this epsilon delta definition encompasses all the limit definitions. But it also does more. For example, we can let S be a set not containing any intervals and still make sense of continuity. For example, we can let S be the set of numbers like 1 over n together with 0. We can ask the question of what is a continuous function on this set using our definition. We will get back to this a bit later in some of the examples. Let's do some examples and start simple. The first two examples are the same as the ones we gave in lecture 2. Here, the domain set S is all real numbers, and we take C to be the origin. The function f sends negative numbers to -1, positive numbers to +1, and 0 to 0. We see that f is not continuous at C. This is because from what we discussed in lecture 2, this function doesn't even have a limit at 0. So it cannot be the case that the limit is equal to the value of f at 0. In fact, no matter what value we choose for f of 0, if we keep the same values of f at non-zero x, the resulting function will never be continuous. Here's another example from lecture 2. The domain S and point C are unchanged. The function is the one where it equals x squared when x is non-zero and 1 when x is 0. Unlike the previous example, the limit of f at C actually does exist. However, the limit is 0, while f of 0 is equal to 1 by definition, and so this function is not continuous. However, if we had defined the function to have f of 0 equaling 0, then this replacement would have been continuous. Now, let's treat a function which we didn't do before. Our domain S is now the open interval from -1 to +1, and C is equal to the origin still. We take our function to be the function that equals x squared times cosine of 1 over x for x non-zero, and f of 0 equals 0. It turns out that this function is continuous at C. Here's how we may check this fact. Let epsilon be positive. Take delta to be root epsilon. Since cosine's output is between -1 and 1, we can evaluate the difference of f of x and f of 0 as the difference between x squared times something that is at most 1 and the number 0. So this difference is no bigger than x squared. On the interval from 0 minus delta to 0 plus delta intersected with s, necessarily we have the absolute value of x is less than delta. And so the value of x squared is no more than delta squared. And hence, with our initial astute choice of delta, this shows that f of x minus f of 0 is no more than epsilon, showing the continuity of f at c. For the next example, we will deal with a case with a more complicated domain. Here, the domain S consists of the points of the form plus or minus 1 over n, where n is a natural number, together with the point 0. Our C is the number 0. We're interested in the following function. When x is 0, we set f of x to be 0. When x is plus or minus 1 over k, we set f of x to be 1 over k times minus 1 to the power k. Notice that with this example, our set S does not contain any intervals. It is just a bunch of points that come together near 0. This function turns out to be also continuous. In spite of its complicated definition, we can show that for elements x of S that are really close to 0, the corresponding values f of x is also close to 0. For this example, given epsilon positive, we will choose delta to equal epsilon. We want to check that the difference between f of x and f of 0 is indeed small when x is close to 0. So first, when x is equal to 0, then of course f of x minus f of 0 is 0. So it is smaller than any positive number. When x is not equal to 0, then since the domain is of the numbers of the form plus or minus 1 over n, there must be some natural number k for which f of x equals 1 over k times minus 1 to the kth power. So we find that f of x minus f of 0 in this case, after taking absolute values, to be exactly 1 over k. So equivalently, we find that the difference between f of x and f of 0 can conveniently be summarized as equaling the absolute value of x. So if x is between minus delta and delta, we must conclude that the difference between f of x and f of 0 is no more than delta, which we have earlier chosen to equal epsilon. So this shows that f is continuous at 0. To summarize this proof, remember that to show a function is continuous at a point C, we need to show that for any given epsilon, we can choose some delta such that the difference between f of x and f of c is less than epsilon, whenever x is between c minus delta and c plus delta. This is exactly what we have shown, that if we take delta to be epsilon, the desired comparison holds true. Let's give one more example before moving on to other stuff. For this example, we will take the domain set to be the integers z. Still, the point c is 0, which is an integer. Our function is the same function from the first example, which gives -1 to the left of the origin, +1 to the right of the origin, and 0 at the origin. Notice, once again, we have a domain that does not contain any intervals. In contrast to what we discussed for the case where the domain is all real numbers, where we found that the function is discontinuous in this case because we have a more limited domain, it turns out that the function is in fact continuous at the origin. We can prove it with the following argument. Let epsilon be positive. We will choose a delta that has no dependence on epsilon. Specifically, we'll choose delta to be 1/2. Since our domain set is only the integers, the only element in the domain that is in the interval from c minus delta to c plus delta is the number 0. No other integers are in the interval from minus 1/2 to plus 1/2. So our requirement that x is in c minus delta to c plus delta limits us to only thinking about x equals 0. But then, of course, f of x minus f of 0 is less than epsilon. The moral of this example is that whether a function is continuous or not depends not only on its formula, but also on which domain you consider the function. Remember from the first initial lectures that a function is not just a formula. The function also incorporates as part of its being its domain and its range. And the domain on which a function is defined does have something to say about whether the function is considered as continuous or not. You will explore this more on the exercise sheet. Let me give one more definition and one more example. Previously, we defined what it means for a function to be continuous at a point C. We can extend this to ask what it means for a function to be continuous on a set S. We say that a function f from some domain S to the real numbers is continuous on its domain S if it is continuous at every point C of the set S. This is pretty straightforward. However, it does add additional complications when you need to check that a function is continuous on a domain instead of just a point x. To illustrate this, let's think about the example where the set S is equal to the real numbers R, and we will consider the fairly simple function f of x equals x squared plus 3. We aim to show that this function is continuous on all of R. The problem, however, is that we need to prove for every possible C in R that there is a corresponding delta that shows continuity. And this delta may depend on both the center C and the tolerance epsilon. So choosing the delta becomes a bit more difficult. Let's do some preliminary computations first. Using the explicit formula for f of x, we can take the difference between f of x and f of c, which we find equals the difference between x squared and c squared, which we simplify to be equal to the quantity x plus c times the quantity x minus c. Now, if we want the difference of output to be less than epsilon, we need to show that the absolute value of x plus c times the absolute value of x minus c is less than epsilon. Now, we haven't chosen a delta yet, but for whichever delta we choose, the value of x minus c is not more than delta. This is what it means for x to be between c minus delta and c plus delta. The value of x plus c, however, is much bigger. At most, it can take the value twice absolute value of c plus delta. When c is positive, this happens when x is just shy of c plus delta. When c is negative, this happens when x is just above c minus delta. And so we know that the product between x plus c and x minus c work out to be no more than twice absolute value of c times delta plus delta squared. If we can choose a delta such that this quantity is less than epsilon, then we are set. At this point, you may be tempted to solve the inequality by using the quadratic formula. That is certainly a valid way to go, but here's a different way which is a bit easier algebraically. What you can notice is that you just need to find a delta that works. You don't need the best delta possible. So, what I can do is to choose delta so that both terms in the sum are each individually guaranteed to be less than 1/2 epsilon. If I do that, then their sum will definitely be less than epsilon. Let's implement this idea. Again, take the center C to be a real number and epsilon positive. I will choose delta to be the lesser of two quantities. The first is the square root of 1/2 epsilon. This would hold delta squared to be less than half epsilon. The second is epsilon divided by 4 times absolute value of c. This would hold delta times twice absolute value of c to be less than half epsilon. So if delta is the lesser of both, then we see that both half of the sum, twice absolute value of c times delta and delta squared, will be less than epsilon halves, and so they add up to epsilon at most. This is what is recorded in step 4. Step 3, which we just skipped, only summarized what we computed in the previous slide. So putting them together, we see that with this choice of delta, indeed, we get that the difference between f of x and f of c is no more than epsilon, if x is between c minus delta and c plus delta. Notice that, as we expected, to choose this delta in step 2, we have to factor in the effect of both the tolerance epsilon and the center c. Okay, this is the end of this week's lectures. Do your exercises, and I will see you next week.